this video, I will show you how to extract the arguments within this system call handler function. This video is a continuation from the last video posted on the course website. You can find the link here. If you haven't watched this video, please watch it before proceeding. So in the last video, we used GDB to traverse up until this point, so you know how the program flow looks like. And now, within this function, how do we get the arguments that we need? If we read the documentation, here it says the system call number is a 32-bit word as the caller's stack pointer. And then the first argument is the 32-bit word as the next higher address, and so on. And how do we find the stack pointer? The stack pointer, ESP, is a member of this argument being passed in. So let's take a look at this struct. Within this struct, we see there's a member variable, which is our stack pointer. So we can get the system call number from this pointer. So here we have a helper function to just help you to get the data from the source address to the destination address. And there's no error checking, but when you do your assignments, you have to check whether the address is legal and so on. And these two helper functions are given in the handout. So now we extract the data from the ESP, and then we put it in this variable I created. And then we try to print out what this value is, right? And we know right now we're testing this function or this test case, right? So it's a write system call, which you can find it here. It's in the user lib here. Write system call. Right? So if we get the correct system call number, it should be the same as system write, right? So here we try to print out what the data we extracted from the ESP, and also we print out what the correct value should be. So next, we will try to get the arguments. The arguments for the write system call will be 3. The first one is the file descriptor, and then the buffer, and the size of the buffer, right? Again, we're using this helper function to get the value from the next higher address, right? So here, if we plus 1 to the ESP pointer, which is a 32-bit word, then we'll get to the next 4-bit, right? And then from the next 4-bit, we'll try to get FD and buffer and so on, right? So we put it in this integer array with the first entry being our FD and the second entry being the address of the buffer, and the last one is the size. So here we also try to print out the data we extracted, and let's see if it gives us the correct output. Let's remake and run this argmin. Okay. So now let's see. System call number is 9 and it's supposed to be 9, right? This is correct because in this enum we can count system write is indeed the 9th element or the 10th element from the 0 index, right? So we get 9, which is correct. Also it should be 9, right? And the FD, because we're trying to just print it out to the standard out, therefore it's just 1 and it should be 1. That's also correct. And the buffer address and the size, right? If you watch the last video, you know these are correct as well. Okay, and then let's continue this program. Okay, once we have this data, we will print out begin, right? And then here we have begin. That's good. And then the next one, we'll try to print out the number of arguments, right? So again, now we have the string that we try to print out in a different size, but it's still a right system call. Therefore, the system call number is still 9, and the FD is still 1 because we're trying to print out to the terminal. But the buffer address, so here it just happens it's using the same buffer, so it has the same address. But then we can see the size is different, right? Because apparently here there are more arguments we try to print out. Okay, but what's the problem? Well, the problem is we know that when we run this command, where is it? Let me make this bigger. When we run this command, where is it? Okay, let me just, yeah. So we only have one argument, which is the program's name, right? So here we're supposed to see argc equals to 1 rather than 0. We know 1 is the correct value, right? Okay, so we can either go into our main function and just simply do a traverse of what's going on. Like there are a bunch of initialization, and later on what we want to see is this run action function. And within this run action, since we are using this run argument, so we'll be executing this function. And since we're in program 2, project 2, so we'll be running this line of code, right? So in process execute, we know once we create a thread, the new thread for this executable, then it will run start process function. But before that, just run GDB. I want to see what is inside of this file name, right? It's supposed to be what we passed in, which is argnet, right? Let's just see that. Okay, let me set up a point at process execute. So this is process.c, line 36. Okay, yeah, I said it before, but doesn't matter. So now we can continue. Okay, we're at run function. Okay, that's in the init I said earlier. Okay, continue. Now we're at line 36 in process.c, right? Okay, let's take a look at what is inside of this file name. args9, right? So this is correct so far. Because right now we're running this test case where the file name is the only argument, right? But if you're running other test cases, you might have other arguments as well. So in this file name, it should list all the arguments that you pass in, right? Okay, let's continue. Then we run the start process for the new thread, and within this, we'll run this load function. And within this load function, we will later on set up the stack, right? Because if we read the documentation, we also know that setting up the stack is what we need to do. Is one of the tasks, right? And also, it says here, the kernel must put the arguments for the initial function on the stack before it allows the user program to begin executing. The arguments are parsed in the same way as a normal calling convention. So this shows you how you should push the arguments onto the stack, right? Here, if we take a look at the default implementation, we added this -12 here earlier just to make the program run minimally, right? But we didn't actually set up the stack. So now we need to set up the stack. Okay, how do we set up the stack? Well, first of all, we need to understand how the stack is laid out, right? Here, the example given to you is a bit more complicated, right? it runs this function, right? So the program's name is ls, and we pass the arguments -l and full and bar, right? Okay. So it's basically saying, you need to push the arguments from right to left. So you push bar first, right? You push bar first, and then full, and -l, and then the first argument, or the file name, whatever you call that. And also all of this has to be terminated by the null terminator. And then you have word align. If it's not aligned by 4, you have word align. And then you just push 0, which I believe they call sentinel, somewhere in here. Yeah, sentinel. Push a null pointer sentinel, which is this 0, and then you push the address, right? This is the address of the let me see, which argument is it? This is FC, right? So this is the address of the rightmost argument, right? FC, and see here, FC, right? And then the second address is the second argument from the right, which is full. This is F8 and F8, right? And so on and so forth. And also, once you push the address of all the arguments, you also need to push the address of where this addresses start, right? So this is D8, here is D8 as well. And then next, you push the number of arguments. Here is 4, right? ls is 1, -l, 2, and full and bar. And then you put a fake address, all zeros, in the very end. So this is a bit more complicated example, but in our example, since our argument is just arg9, so we only have one argument, and then you do the word align and the sentinel value. And what we want to solve here, remember our problem is try to get the argc, the number of arguments, correct, right? Right now it's we showed it earlier, right? Right now it's 0, but it's supposed to be 1, right? So it means this value currently is 0 for us, but it's supposed to be 1. Okay. Now let's do a quick spreadsheet. So we can let's do the basically let's just kind of do a similar operation, pushing our arguments onto the stack, right? So now we need to push arg none. The last because we look from right to left, so this is null terminator first, right? And then arg none. So because the stack grows backwards, that's why on the top is higher address and at the bottom is lower address. Arg none, so it's N-O-N-O-N-E, right? And then dash and args, A-R-G-S, right? Args none. And then next we do word alignment, right? So aligned by 4. Right now we have 1, 2, okay, right now we have 10, right? So if it's aligned by 4, then we need to do 2 paddings, 2 zeros here. So it's at offset 12. So now 12 is a multiple of 4, right? So word alignment is correct here. So it's not always necessary, right? In this case, we need 2 word alignment. But then in some other case, if your arguments, once you push them on the stack, if they have the length of the multiple of 4, you don't need to do word alignment, right? But just in this example and in the given example, it just happens that we have to do word alignment. So next, the argument, the address of the first argument, since we're going to have one address, so the address of the argument is this F6, right? BF, FF, FF, F6. Okay, so now let's do this BF, FF, FF, F6, F6, right? Remember this value corresponds to this value, or I mean this entire thing, right? Because here it's supposed to be like, you know, BF, FF, FF, F6, right? I just didn't write the first several digits. Okay, now we also push the argument address. Now the next one is the address of the argument address, right? So the address of the argument address is from this F0. Okay, again we need to do BF, FF, FF, and F0, right? Okay, then next, the number of arguments. The number of arguments is 1 in our case. So we need to put 1, but it takes like an integer, so 4 bytes. Sorry, yes, so 4 bytes, right? That will be 0. That will be 0, 0, 0, 1, right? And then the last one is just return address, another 4 bytes of zeros. So 0, 0, 0, 0. Okay. Let me see whether this is correct. Well, how to? Okay, let's align this, and let's see if there is something we missed. Is this correct? Yeah, so I did the calculation earlier. Let's just compare. Okay, let me delete this column. Okay, so okay, apparently I'm missing 4 bytes. What other 4 bytes? Oh, okay, right, I missed the sentinel value, right? After this alignment, see here, after this alignment, right, there's supposed to be 4 bytes of sentinel values of zeros. I forgot to do that. Alright, so now let me just move this down by 4. Well, in that case, okay, in that case the address will be incorrect. Okay, this shows you, you know, when you do the calculation, you have to be very careful, right? So I made a mistake here. So here is supposed to be another 4 bytes of sentinel value, and then we try to get the address of the first argument, which starts from F6, right? So it will be BF, BF, FF, FF, F6, right? So these two correspond to each other, F6, right? And then later on, we want to get the address of the argument address, which is this EC, right? So it's BF, FF, FF, EC. EC and this EC, they correspond to each other, right? And then it will be the number of argument, which is 1, so 1, right? And the fake return address, which is 0 again. Okay, so this time it's the correct layout as the one that I calculated previously, right? Everything lined up perfectly. So I suggest you, if you're setting up your stack, you can also do a spreadsheet like this, or just write it on paper, so you know the calculation won't mess up, right? Because, you know, when I was doing it here, I messed up once. I forgot the sentinel value, right? Okay, now with this, we can set up our stack. So here, we want our ESP to be pointing to like where our data is, right? So our data is actually starts 32 bytes below physical base, right? So with that saying, rather than minus 12, we need to minus 32, okay? And then where do we actually want to set the number of argument? We want to set the number of argument at this address, E4, right? Or the ESP pointer, right now that ESP pointer is pointing to this location, ESP, or this address. So if we use ESP pointer plus 4, right? 1, 2, 3, 4, right? Plus 4, then this byte we want to set it to be 0. Okay, so I can do that by using memory set and ESP plus 4, right? And we want to set it to be 1, and we only want to set this 1 byte to be 1, right? Okay, let's see if this is the correct way to use memory set. Okay, set this byte in the destination to value, right? So here we set 1 byte at this destination to be the number 1, right? So it's correct based on this layout here. Okay, now if we run the program again, we're supposed to see the number of argument to be 1 rather than 0. Let's see if that's the case. Let's run make. Okay, return. Okay, forget this. Oh, I have auto format on. All right. Okay, now let's run the program without GDB. See here, our argc is 1, as it should, right? But then we still have page fault. Why? Because I only set up this 1 byte. However, for you need to set up all these information on the stack correctly, right? So here I just want to show you an example. Right, your project, right? You don't want to hard code everything, right? You should like analyze what's inside of the file name, right? And then parse this string, and then later on push onto the stack accordingly, right? And also, as you can see, setup stack only has 1 argument. So somehow, you might add another argument here, or you might do something else to have the data in the file name passed into this function. That's how you can properly get all the data that you need to set up your stack, right? And before we finish, there is another function that you can use, which is called hexdump, right? Hexdump. This is a function that can help you to debug, especially when you are working on the stack setup. Let me show you how you can use it for your debugging purpose. Okay, so now I want to see, okay. Now I want to see these from physical base minus 32, and a buffer is just my ESP, and then size is 32. I want to see the ASCII value. Okay. So this hexdump, I think it also mentioned in the documentation, right? Basically, it gives you the information about what's on the stack at a certain address, right? Or I mean, you specify the buffer address, and then it will show you what's inside of the buffer, right? So if you just specify you want to look at wherever the ESP is pointing to, then you can look at whether you set up a stack properly. Okay, so this is our stack currently, right? If we compare with the one that we calculated manually, we'll see, okay, this from E0 it's 0 0 0 0 4 0 and then 0 1, right? So from E0 we have 0 0 0 0 4 0, and then the next one is 1. This one is 1, right? So right now, because I only set up this 1 byte on the stack, therefore it's 1. So only this byte is correct. So after you implement the code, right, all these bytes should look the same as how we did it manually. Right? That's how you can verify whether it's correct. And also, if it's correct, you should be able to just pass this argnet test case. Alright, yeah, I think with this help, it should be easier for you to get started with Project 2. And yeah, good luck.